Ray tracing on its own isn't exactly new. It's existed for quite a long time. What is new is that a graphics card manufacturer names an entire lineup of graphics cards after it, which is why everyone's talking about ray tracing now. And so I thought to myself, this is the perfect moment to make a video about what ray tracing actually is and why you would want to use it. So, what rendering means in the world of computer graphics is that the computer gets some sort of description of a 3 or 2-dimensional thing, and then uses that description to actually generate an image that will appear on a screen. So, a very simple form of rendering would be that I told you, draw a circle with a radius of 5 centimeters, and if you then draw that circle, you're effectively rendering it, right? I gave you a description of it, and then you rendered it. You turned that description into an actual circle. Well, that's what rendering is in a computer. In a computer, the CPU or the GPU, most of the time it's the GPU doing the rendering, gets a mathematical description of a situation. This can be 2-dimensional or 3-dimensional, and then it turns this description into an image that we people can actually look at. If I would want to render this roll of tape on a computer, what I would do is I would subdivide this roll of tape into a number of polygons, which are basically triangles. All of these polygons have corners, which we call vertices, and then the coordinates of these vertices, so the location of each vertex in space, all of these coordinates, those would be sent to a graphics processor, for example, and it would then use these coordinates to build up an image of that roll of tape. So that's the very basic idea of rendering. But as you've probably guessed, there are many different ways in which this can be achieved. There are many different techniques that you can use to do this. And one of these techniques is ray tracing. So ray tracing is a way of turning a description of something into a real image. The fundamental idea of ray tracing is that we do this by simulating how an image is created in the real world. So let's say you have a 3D situation, a landscape, for example. You're taking a picture of that landscape with a digital camera. Now, the way the picture is taken is light from the sun, for example, or some other light source. Light rays from a light source enter the scene. These light rays then bounce around in the scene. They reflect off objects, and eventually some of these light rays will be reflected in the direction of the camera. They will then go through the lens of the camera, and they will be projected onto the image sensor. And the image sensor is a grid of pixels, and each one of these pixels detects light and also detects the color of this light, and that will then build up the image, basically. So ray tracing attempts to simulate this whole process in a computer, because the idea is that if we simulate how an image is created in the real world, then we technically are able to create a real image. We are technically able to create an image that looks exactly like the real world. That's the whole idea behind it. So then how do we do it? How exactly do we do it? Do we simply simulate all the light rays going from this light source and simulate them reflecting around the scene and going into the camera? Well, no. Because as you can imagine, a light source emits a lot of light rays which all go into this scene, but only a small portion of them, a small part of these light rays, eventually reaches the camera, because the camera is only a tiny, tiny device compared to, let's say, the size of a landscape. So only a very small amount of the light rays that enters the scene actually ends up in the camera, which means if we would use all of our processing power to simulate all of these light rays, which would take a lot of processing power, and then we're only using 1% of that, because those are the light rays that actually end up in the camera, then that's kind of a waste, right? That's not very efficient. So what we're doing instead is we're tracing the light rays, we're simulating them backwards from the camera instead, from the camera to the light source, because that way we can simulate only the light rays that need to be simulated, only the ones that actually affect the image of our camera. So here I've got a schematic drawing of a situation that we're going to render using ray tracing. So first of all, we've got three objects, objects A, B and C, which are of course virtual objects defined as a bunch of coordinates in space. Then we've also got a virtual light source, as you can see, that's the yellow dot, and finally a virtual camera. The virtual camera consists out of two parts, which is the so-called eye point and the raster. The raster, also referred to as image plane, is a grid of pixels that is going to be our final image. So that's going to be the result of the rendering. Now, in my example, it's just a small grid, but of course in the real world, this will be something like 2 million pixels. This will be the size of a display, because otherwise your image won't look very good. And then the eye point is the point from which we're going to trace the rays. So it all starts off by tracing a ray from the eye point through the first pixel of our grid, through our raster. So then we'll get a certain line that goes into the scene, and now the next thing that we need to do, what the computer needs to do, is it needs to check if this line intersects with every one of the objects. So first of all, it's going to see, well, does this line intersect object C? Well, no, it doesn't. Does it intersect object B? No, it doesn't. Does it intersect object A? Yes, it does. So it goes through all the objects in the scene, and then it sees with which objects are intersected by this line. And as you can imagine, this takes some time when there are loads of objects in the scene. Alright, so it's now detected that the line intersects object A. Then it calculates where this intersection takes place within the scene, so it finds the coordinates of this intersection point. The next step is to look up what the colour of this object is. So with the rendering, we just talked about how it turns a description into an actual image. It doesn't just get coordinates of the objects, it also knows what the colour is of the objects, or the texture, for example, or whether it's transparent or whether it's reflective, etc. So it looks up the colour in the data sheet and it sees, oh, object A is green. Well, that's simple, let's turn this pixel green. Okay, done, right? Simple. Well, yes, we could simply call it a day and say this pixel is green, done, which is called ray casting. This technique is what we would call ray casting. So with ray casting, you're just tracing one line through one pixel, and then it hits an object, you determine the colour of that object, and then you're done. With ray tracing, we go slightly further. So we can see that this object is in fact a reflective object, which means that we also need to calculate the angle at which our first ray hit the object, which allows us to construct another line like so. So a reflection line. And we can see, oh, that reflection line ends up in the light source, so our pixel just stays green. Or maybe, if it's a very glossy object, it might directly reflect the light source like a mirror, and then the pixel might be yellow or bright white because of the direct reflection, but that doesn't really matter for now. Alright, so it's done now. That went pretty fast, so now it goes on to the next pixel, so it traces another line. Oh, it intersects with object A again, so the pixel will become green. But then again, object A is reflective, so a reflection line is then constructed, which turns out to intersect with object B, which is a blue object. That's interesting. So this pixel doesn't see a green object. This pixel, in fact, sees a reflection of a blue object that is reflected by a green object. So Therefore, this pixel will now become, I don't know, some kind of blue-greenish mix. And then we can trace the ray further to object C and towards the light source and so on. And so every time this light ray intersects with another object, that's going to affect the colour of our pixel. And this is the key to why ray tracing can produce such realistic images, because this allows it to create realistic looking shadows, mirroring effects, etc. And that can create very photorealistic images. The disadvantage is that it takes quite a long time to render images this way, at least on today's computers. Because in our example we had just a couple of objects, we had a small grid of pixels, and we had one light source. But in the real world of real ray tracing, you're going to have a massive grid of pixels because it needs to be high quality, you're going to have multiple light sources, and finally you're going to have loads of objects in the scene. So because ray tracing takes a lot of processing power and time, it's often used for non-real-time rendering, which means rendering animations or CGI effects, stuff like that. For real-time things like playing a game where you need to render the frames fast, I mean, when you're playing a game you want 60 frames per second, right? Because you want to be able to eliminate your opponent quickly. So you need those frames to be rendered fast, and ray tracing is not the most suitable rendering technique to achieve that result. But now there is this interesting video card lineup coming up from NVIDIA. So what they've apparently done is created a lineup of graphics cards that is optimized for ray tracing, or at least is much better at ray tracing than existing graphics cards. And they're aiming to apply this ray tracing in real-time applications. Anyway, this video was not about these graphics cards. It's also not sponsored by NVIDIA, by the way. Perhaps ray tracing works better on AMD cards, who knows. But anyway, now you know more about what ray tracing is. I hope you've enjoyed this video, and of course, thank you for watching.